Okay, so in this video, we are going to consider our first optimization problem. If you look on the problem sheet, this is the second problem. So let's look at the question. We want to find a positive number such that the sum of the number and its reciprocal, so 1 over the number, is as small as possible. So let's see, we want a positive number, call it x. So x is bigger than 0. And we're trying to minimize the sum of the number itself and its reciprocal, so x plus 1 over x. So let's write down this is f of x, and then our interval will be for positive real values, so from positive and from 0 to positive infinity. And we want to minimize this quantity. And I'll just simply write min for minimizing. We want to minimize the function f of x, being x plus 1 over x. And what is our interval for the x values? I'll write int for interval. Because x ranges from 0 to positive infinity, x being positive, our interval is from 0 to positive infinity. So that's the range of our x values. Now, we know that if we have a continuous function on a closed and bounded interval, to find the max and min of this function, we simply have to evaluate the function at the endpoints of the interval and at the critical points inside of the interval. And this gives you the quickest way to maximize and minimize a function over a given closed and bounded interval, if that said function is continuous. Well, if you look at this function, the only problematic point would be when x is 0, because a 1 over 0 will give you a vertical asymptote. But as you can see, we are rejecting 0, right? We're starting with a strictly positive value of x, so we exclude 0. So on this interval, since we are staying away from 0, the function f of x is continuous. The problem is the interval is not bounded. We go from 0 to positive infinity. So we cannot use our result. And the question is, in a case like this, how do you then minimize, in our case, or maximize a function? And the idea is simply produce a very rough sketch of the graph of the function. And then you'll be able to see from your sketch if there is a minimum and or a maximum. As always, we need to find if we want to produce a rough sketch of the graph, and keeping in mind, why am I saying rough? Our goal here is not to sketch the function of f accurately, but simply to figure out where there may be a minimum or a maximum. So we will find the first derivative, so f prime. Well, if you want to differentiate this, you can simply rewrite the 1 over x as an x to the negative 1. So the derivative of f will be 1 minus x to the negative 2. Find the second derivative, f double prime, to give you concavity, which is the derivative of 1 is 0, minus negative 2, so positive 2, x to the negative 3. You can rewrite both using positive powers of x, so the first derivative ends up being 1 minus 1 over x squared, and the second derivative simply 2 over x cubed. Let's find our possible critical points. Those are points where the derivative is undefined or 0. Well, the derivative would be undefined if x were allowed to be 0. As we are excluding 0 from our interval, the derivative will always be defined. So we're looking for values of x where the derivative is equal to 0. So let's solve for x. Send 1 over x squared on the other side. And this gives you 1 is equal to 1 over x squared. Multiply by x squared, and you'll get x squared is equal to 1. Therefore, x is either plus or minus 1. So x is negative 1 or positive 1. But we're looking for values of x on the interval from 0 to infinity, excluding 0. Clearly, negative 1 is not part of the interval, so we reject this value. And we have a unique critical point on the positive real axis, x equals 1. So we have only one critical point. The question is, well, what does the curve look like at this point? Do we have a local maximum, in which case the curve would be concave down, or do we have a local minimum, in which case the curve is concave up? Well, if you notice, we have our second derivative here, 2 over x cubed, and because x is always positive, x cubed is always positive, therefore 2 over x cubed is always positive. So because x is only allowed to be strictly positive, the second derivative at any given positive value of x is also positive for any x. Well, if the second derivative is positive for every value inside of our interval, the curve is always concave up. And the key word here is always. For any positive value of x, the second derivative is positive, therefore the curve is always concave up. Well, the curve is always concave up, and at x equals 1, since the derivative is equal to 0, the curve is flat at x equals 1. So we know what the curve or the graph of this function would look like. We can now produce our rough sketch. Let's recall that f of x was simply x plus 1 over x. So we only consider the positive real axis, as our range of x values is for positive real values. And we look around our unique critical point when x is 1. F of 1 will be 1 plus 1 over 1, which is 2. So we have this point. This is a critical point, as we have just said, where the derivative is 0. So the curve is flat there. And the curve is always concave up. So it has to look like this. And what's great is, this is the only critical point. And if you look at the second derivative, which is 2 over x cubed, could we ever have an inflection point or by the second derivative being 0? Well, no, because 2 is non-zero. And because we are avoiding the value x equals 0, the second derivative is always defined. So confirmation that the curve will always be concave up. So if you look at your graph, really rough sketch of the graph of x plus 1 over x, since there are no other critical points or inflection point, the curve will never change its behavior again. It will always look like this. And so if you notice, we have just found our absolute minimum. And you can replace the word absolute by global. They are synonyms. So this is the absolute slash global minimum of the function. And what was the question? If you remember, the question was to find a positive number x such that the sum of the number x plus its reciprocal, 1 over x, is as small as possible. So we were asking for a value of x that is positive so as to minimize this function. So we were trying to minimize the function x plus 1 over x for strictly positive values of x. And now we have just done so. By producing a rough sketch of the graph, we found that the function is minimized when x equals 1. And the minimum value is 2. So the real number, whose sum between itself and its reciprocal is minimized, is simply x equals 1. And that is our answer. And that's basically the core of optimization when you have either a function that is discontinuous or an interval that is not closed and bounded. You have to, in order to find your minimum or maximum value, just producing a rough sketch of the graph of the function you're trying to maximize or minimize. In our next video, we'll consider a simple example, such as this one, but where we will have a continuous function over a closed and bounded interval. That way, we can produce a much nicer solution. We will not have to sketch the graph of the function because we know we can find the max and or min simply by evaluating the function at the two endpoints of the interval and at the critical points inside the interval. And this way we will find the maximum and minimum value of the function. And this will be in our next video.